Hi guys! Stat Lessons here, another 20 questions session for you. This one's centered on AI search configuration, AI gateway guardrails, and retrieval evaluation metrics. Same format as always. Question, countdown, answer, explanation. Pause anywhere you need to think. Enjoy. Time for another one. Question 1. Compare scope and condition. A generative AI engineer discovers that their production inference table has completely stopped capturing new requests. Investigation reveals that a data engineer recently renamed the delta table backing the inference table to conform to a new naming convention, and also applied a schema change to add a new audit column. What are the two root causes of the logging failure? Select 2. Review the answer choices on screen. The correct answers are option A and option B. 3 operations break inference tables, 2 distractors don't. Inference tables have 3 documented operations that cause logging to stop or become corrupted: renaming the backing delta table, changing the table schema, and deleting the table. Renaming the delta table breaks the endpoint's stored reference to the storage location, immediately halting all logging because the endpoint can no longer find its target. Changing the schema, such as adding a new audit column, corrupts the inference table because the endpoint expects a fixed schema and cannot reconcile the new column structure. A sampling fraction below 1.0 causes intentional probabilistic sampling of requests rather than a logging failure. The table continues operating normally for the sampled fraction. Hitting the 128 concurrent request limit affects request queuing and throttling behavior, but does not cause the inference table to stop logging. Exceeding the 10 MB payload limit prevents those specific oversized payloads from being logged, but does not halt the inference table's operation for all other requests. Let's dig into this one. Inference table failures have a very specific set of triggers worth knowing cold. Imagine a data engineer renames your delta table to match a new naming standard, then adds an audit column. Sounds harmless, but the next morning, your inference table logs are blank. Here's why. The endpoint holds a hard reference to one specific table path. Rename it, and the reference snaps. Add one new column and logging stops. The endpoint expects a fixed schema. The distractors sound scary, but they're red herrings. Sampling below 1 means intentional skipping, not failure. The 128 concurrent request cap throttles traffic, not logging. The payload size limit blocks one oversized request, not everything. The question rewards knowing the 3 killers: rename, schema change, delete. Ready. Question 2. Translate the story into requirements. A generative AI engineer Advantage Research is building a RAG application over a corpus of lengthy scientific papers. Users require precise fact retrieval but also need the LLM to generate answers informed by the broader surrounding text, rather than just the specific matched passage. Which chunking approach best satisfies both requirements simultaneously? Select 1. Review the answer choices on screen. The correct answer is option D. Small chunks search. Large parents answer the question. Parent-child retrieval directly addresses the dual requirement of precise retrieval and rich context. Small 512 token chunks are indexed and searched, giving the retrieval step a tight semantic focus that pinpoints the most relevant passage. When a chunk is matched, its larger parent segment of approximately 2048 tokens is retrieved and passed to the LLM, providing the surrounding context needed for well-reasoned answers. Semantic chunking produces coherent variable size segments, but does not include a mechanism for automatically expanding the context window beyond the matched segment when passing content to the LLM. Fixed size 1024 token chunks improve context breadth but reduce retrieval precision because more surrounding text is co-embedded within each indexed unit. Recursive character splitting with 256 token chunks maximizes retrieval precision, but passes only the small matched chunk to the LLM, depriving it of the broader contextual material needed for thorough answers. Ready? Question 3 is up. A generative AI engineer at Northgate Manufacturing is deploying an internal LLM assistant used by 2,000 engineers across multiple teams. A small number of engineers with automated scripting workflows generate extremely high query volumes during peak project deadlines, causing degraded response times for all other users. Which AI gateway feature should the engineer configure to address this? Select one. Review the answer choices on screen. The correct answer is option D. 1 feature caps per user consumption at the gateway. Rate limiting enforced at the user level caps how many queries per minute or tokens per minute any single user can send, preventing automated workflows from monopolizing endpoint capacity during peak hours and ensuring fair throughput for the broader engineering organization. This directly addresses the scenario where a few heavy users degrade performance for everyone else. PII detection and redaction scans for personally identifiable information and replaces it with placeholders. It has no effect on request throughput or resource fairness across users. Safety filtering blocks harmful content categories such as hate speech and violence and is a content quality control, not a resource allocation mechanism. Traffic splitting distributes requests across multiple model endpoints for A/B testing or gradual rollout, but does not limit how much capacity any individual user is allowed to consume. Let us switch gears. Question 4. Test each option against the full ask. A generative AI engineer is building a technical support knowledge base retrieval system for a software company. Support agents search using both exact product error codes and natural language descriptions of customer problems. The engineer configures a Databricks AI search index to handle both query styles effectively using hybrid search. Which two components does Databricks AI search use to implement hybrid keyword plus semantic search? Select 2. Review the answer choices on screen. The correct answers are option D and option E. Name all 3 hybrid components to get full credit. Databricks AI Search Hybrid Search combines 2 distinct retrieval mechanisms. OCopy BM25 handles the keyword search component by scoring documents based on term frequency and document length normalization, making it effective for exact product error codes and specific technical terms. HNSW-based approximate nearest neighbor search handles the semantic component by finding vectors close to the query embedding, enabling natural language queries about problem descriptions. The results from both searches are merged into a single ranked output using reciprocal rank fusion with a default RRF_param of 60, which combines the ranked lists without requiring the BM25 and vector scores to share the same scale. TF-IDF is an older keyword scoring approach not used in Databricks AI Search, which uses BM25 instead. PageRank is a link-based ranking algorithm designed for web graphs and is unrelated to text and vector document retrieval. Euclidean distance is the underlying L2 metric used by HNSW for vector comparison, but naming the distance function alone does not describe the full hybrid system. The complete answer requires naming both the keyword algorithm and the fusion method. Here's a tricky one. Let's break apart exactly how Databricks AI Search does hybrid search. Imagine a support agent searching for exact error code ERR_con_reset. Now another types my connection keeps dropping. Same system, totally different styles. Databricks AI Search uses 3 real pieces. BM25 is the keyword scorer, term frequency plus length normalization. HNSW, a graph-based vector index, finds documents close in meaning. RRF, reciprocal rank fusion, merges both ranked lists by position, not raw score. 3 distractors hide in the options. TF-IDF is an older scorer BM25 replaced. PageRank ranks web pages by links. Wrong domain. Euclidean distance just names HNSW's measuring stick, not the full system. D and E are the real pipeline. Those are your 2. Let us switch gears. Question 5. One detail changes the answer. A generative AI engineer is designing an AI search solution for a news organization where new articles are published continuously throughout the day. The index must reflect newly published content within minutes of publication without any manual pipeline triggers, and the team wants Databricks to handle all embedding computation automatically. Which index configuration should the engineer use? Select one. Review the answer choices on screen. The correct answer is option B. Managed sync still needs a change tracking mechanism underneath. A delta sync index with Databricks managed embeddings is the correct choice when the goal is fully automatic synchronization without team-managed embedding computation. When new rows are appended to the source delta table, AI search uses change data feed to detect the additions and automatically computes and indexes the embeddings. No manual triggers, SDK pushes, or custom pipelines are required. A direct access index requires the calling application to explicitly supply embeddings via SDK calls for every new document, meaning the team must manage embedding computation themselves and trigger a push for each publication event. A storage-optimized endpoint is an infrastructure configuration for cost efficiency at large scale and does not change how embeddings are managed in a direct access index. A delta sync index with self-managed embeddings still requires the publication pipeline to compute and write embedding vectors to the source table before changes are reflected in the index, which does not satisfy the requirement for Databricks to handle embedding computation automatically. The first 5 questions spanned inference table failure modes, parent-child chunking for RAG context, AI gateway rate limiting, and AI search hybrid architecture, CDF, BM25, HNSW, and RRF all in the same block. Keep your focus here. Question 6. Start with what the user needs. A generative AI engineer is building an e-discovery application for a law firm. Users frequently search for documents using exact case names, statute codes, and specific Latin legal phrases that must be matched literally. However, users also ask conceptual questions where the relevant documents use different phrasing from the query. The retrieval layer must handle both patterns reliably. Which configuration should the engineer implement? Select one. Review the answer choices on screen. The correct answer is option B. Legal queries mix exact and conceptual. Neither alone suffices. Hybrid search in Databricks AI Search combines BM25 keyword matching with vector similarity search and merges both result lists using reciprocal rank fusion, RRF. BM25 reliably handles exact match queries for precise legal terms and statute codes, while vector similarity captures conceptual or paraphrased queries where document wording differs from the user's query. RRF blends the two ranked lists without requiring hand-tuned relative weights. Relying solely on vector similarity with metadata filters is insufficient because metadata filters are hard predicates on structured fields, not a mechanism for matching arbitrary legal phrases within document text. Using only BM25 handles exact terms well but fails on conceptual questions where vocabulary diverges from the query. Maintaining two separate indexes with a classifier adds significant operational complexity and assumes query intent can be cleanly categorized, which is unreliable for legal queries that often blend both patterns. All right, question 7. The wording is the clue. A media company is building a content discovery platform that recommends articles to users based on their reading history. The system must identify whether a new article is semantically similar to articles a user has already read. comparing thousands of stored article vectors against a new article. The system must not generate any new text. Which type of model should the engineers use? Select one. Review the answer choices on screen. The correct answer is option D. No text generation disqualifies every generative option here. Semantic similarity comparison between articles is a retrieval task that requires fixed dimensional vector representations, not text generation. Embedding models like BGE large convert text into dense vectors that can be compared efficiently using distance metrics in a vector store. The system explicitly does not require generating new text, making generative LLMs inappropriate regardless of size or fine-tuning. Dbrx instruct is a generative instruction following model that produces text output and cannot produce the fixed vector representations needed for similarity indexing. Code Llama 34B is a code-specialized generative model with no capability for producing semantic embeddings of editorial content. A fine-tuned generative LLM still produces text output rather than embedding vectors and cannot directly index or compare documents in a vector store. Alright, question 8. The scenario tells you the trade-off. A generative AI engineer at Lakeshore Digital is deploying a content moderation pipeline for a social media platform with 5 million daily active users. The pipeline runs continuously and must sustain approximately 2,500 posts per second at peak load. The team operates under a fixed monthly inference budget and requires predictable costs. Which serving configuration should the engineer select? Select one. Review the answer choices on screen. The correct answer is option A. Fixed budget plus sustained load always points to provisioned. Provisioned throughput endpoints allocate dedicated inference capacity that scales with configured minimum and maximum token throughput parameters, guaranteeing consistent performance under sustained high volume load, and generating a predictable fixed monthly cost that aligns with the team's budgetary constraints. Databricks recommends provisioned throughput for all production workloads requiring performance guarantees. A serverless custom model endpoint that scales to 0 introduces cold start delays when traffic resumes after quiet periods, creating unpredictable latency spikes in what must be a continuously running pipeline. Pay-per-token foundation model API endpoints are not designed for always-on high-throughput applications. They lack dedicated resources and latency guarantees under consistently heavy load, and their variable token-based costs are ill-suited to a fixed monthly budget. An external model endpoint introduces a dependency on a third-party provider with additional network round trips and cannot deliver the reserved capacity needed to maintain guaranteed throughput at this scale. Alright. Question 9 is next. A generative AI engineer at Norgate Systems has been developing a document classification model using the MLflow Logged Model API, accumulating metrics, parameters, and execution traces across multiple development iterations. After completing development, they promote the logged model to a Unity Catalog model version. What happens to the performance data collected during development? Select one. Review the answer choices on screen. The correct answer is option C. Promotion carries every metric and trace forward automatically. When a logged model is promoted to a Unity Catalog model version, all performance data, including metrics, parameters, and traces accumulated across every development iteration, automatically becomes visible on the UC model version page. This seamless promotion is a core capability of MLflow 3's integration with Unity Catalog, ensuring that the complete development history is preserved and accessible for governance, reproducibility, and auditing without any manual migration step. Metrics are not archived to DBFS during promotion. They remain linked through the MLflow tracking backend and are surfaced in the Unity Catalog interface automatically. Intermediate iteration metrics are preserved in full alongside final metrics, not selectively discarded during promotion. Performance data does not remain isolated in the originating MLflow experiment. It becomes fully accessible through the Unity Catalog model version page as a direct result of the promotion. OK. Question 10. Pick the complete answer. A generative AI engineer is building a real-time product recommendation assistant using Databricks Feature Serving. The system needs to retrieve a customer's purchase history and loyalty segment from a pre-materialized feature table, and also compute a real-time affinity score by applying a registered Python UDF to those features at inference time. Which two FeatureSpec components should the engineer use? Select 2. Review the answer choices on screen. The correct answers are option A and option C. Retrieve the stored value. Compute the derived one on demand. Feature lookup retrieves pre-computed feature columns from an online feature store table at inference time, which is how the engineer pulls the customer's purchase history and loyalty segment. Feature function applies a registered Python UDF to features at inference time, enabling on-demand computation of derived values like the real-time affinity score. Together, these two components cover the full FeatureSpec requirement: materialized retrieval plus on-demand transformation. Feature query is not a valid component of the FeatureSpec API. Feature transform is not part of the FeatureSpec data model. Feature monitor is unrelated to inference time feature computation and does not exist as a FeatureSpec component. Questions 6 to 10 covered embedding models versus generative LLMs, provisioned throughput for predictable production budgets, MLflow logged model promotion to Unity Catalog, and the FeatureSpec 2-component retrieve then compute pattern. Here we go. Question 11. Read this one twice. A generative AI engineer at Southridge Electric has created a delta sync index in Databricks AI Search and now wants to wire it into a LangChain Q&A chain. The chain should retrieve the 5 most semantically relevant document chunks for each user query and pass them to the generation model. Which LangChain object should the engineer instantiate to connect the AI search index to the retrieval step of the chain? Select 1. Review the answer choices on screen. The correct answer is option A. The LangChain wrapper matters more than the raw API call. Databricks Vector Search is the LangChain integration class that wraps a Databricks AI search index and exposes it as a standard LangChain retriever, instantiating it with the index name and calling as _retriever with k equals 5, returns the 5 most semantically relevant chunks for each query and passes them downstream in the chain through the standard retriever interface. Databricks Embeddings converts text to vector representations for embedding queries or documents during indexing or standalone similarity tasks. It is not itself a retriever and cannot serve as the retrieval component of a Q&A chain. Using vector search client with similarity_search inside a custom tool works at the API level, but bypasses the native LangChain retriever interface, adding unnecessary boilerplate and losing interoperability with standard chain abstractions. Chat Databricks is the LangChain wrapper for an LLM serving endpoint that handles text generation, not retrieval, and has no mechanism to query an AI search index. Next up, question 12. Classic exam trap. A generative AI engineer has trained multiple candidate models for a customer intent classification system and registered them in Unity Catalog as versions under a single registered model path. A junior engineer asks how to identify the model currently serving production traffic and how to safely promote a new candidate without modifying inference code. Which two capabilities of the Unity Catalog model registry address these needs? Select 2. Review the answer choices on screen. The correct answers are option A and option D. Aliases route traffic. The UC page exposes development history. Unity Catalog Model Registry uses aliases such as champion and challenger to provide stable, human-readable pointers to specific model versions. Serving code references the alias rather than a hard-coded version number, so promoting a new model requires only reassigning the alias without redeploying application code. When a logged model is promoted to a Unity Catalog model version, all performance data, metrics, parameters, and traces captured during development automatically appear on the UC model version page, giving stakeholders full visibility into the model's provenance and evaluation history. Experiment tags describe runs within experiment tracking and do not serve as a production routing mechanism. Unity Catalog Model Registry uses aliases for version management, rather than the staging and production stage-based lifecycle states that belonged to the legacy MLflow Model Registry. Automatic retraining is not triggered by alias reassignment. Let's slow down on this one. Aliases and model version tracking are worth understanding properly. Imagine your team has trained 5 versions of a customer intent classifier. Version 3 looks best, but your serving endpoint is already live. You don't want to redeploy it. Aliases solve this. You label version 2 as champion and version 3 as challenger. The endpoint just asks for champion and never touches a hard-coded version number. When you're ready to swap, you reassign the alias. 0 code changes. Meanwhile, the Unity Catalog model version page shows up once you register a trained model. It surfaces every metric, parameter, and trace from that training run. The question dangles lifecycle stages like staging and production. Those belong to the old MLflow registry. Unity Catalog dropped them. Aliases plus the version detail page. Those are the 2 answers. Next up, question 13. The trap is partial correctness. A generative AI engineer at Pinecrest AI is building a feature-serving endpoint that must both retrieve a pre-materialized customer activity score from a feature table and compute a derived risk category by applying a custom UDF that combines the retrieved score with a value provided at request time. Which 2 feature spec components should the engineer use for these 2 operations? Select 2. Review the answer choices on screen. The correct answers are option A and option C. Same 2-component pattern in a riskier serving scenario. FeatureSpec supports 2 component types with distinct responsibilities. Feature lookup retrieves pre-materialized column values from a feature table by joining incoming requests on entity keys, making it the correct component for fetching the stored customer activity score. Feature function applies a registered Unity Catalog Python UDF at request time to compute derived values, making it the correct component for calculating the risk category by combining the retrieved score with the runtime input. Feature index does not exist as a feature spec component type. Feature pipeline is not a feature spec component. Ingestion pipeline orchestration is handled separately from the serving specification. Feature transform is not a feature spec component. Schema transformations and derived calculations at serving time are handled within feature function. Next up, question 14. Let the constraints drive the choice. A generative AI engineer at Haverford Research is building a RAG application for medical literature search. Clinical users need to retrieve all relevant studies related to a patient's condition before forming treatment decisions. Missing a relevant study could directly harm patient outcomes. The engineer is selecting the primary retrieval evaluation metric. Which metric should they prioritize? Select 1. Review the answer choices on screen. The correct answer is option A. Safety-critical retrieval means completeness beats ranking quality. Recall at K measures the fraction of all known relevant documents that appear within the top K retrieved results, directly quantifying completeness. When a missed document carries clinical risk, Completeness becomes the overriding requirement, making recall the correct primary metric. A recall value of 1.0 confirms that every relevant study was surfaced. Any value below 1.0 represents a document the system failed to retrieve. Precision at K measures the proportion of retrieved results that are relevant, which optimizes for a clean reading list rather than ensuring no relevant study is omitted, the wrong trade-off in a safety-critical setting. NDCG at K evaluates ranking quality by rewarding systems that place the most relevant results higher, but it does not capture whether all relevant documents were retrieved at all. DCG at 10 similarly measures graded ranking quality within a fixed window and shares the same gap. A system could achieve a high DCG at 10 while still missing relevant studies that fall outside the top 10. Now, question 15. Avoid the familiar but wrong answer. A generative AI engineer has prepared a delta table containing chunked product documentation with a unique chunk ID column and a text column for embedding. When attempting to create a delta sync index on an active standard Databricks AI search endpoint, the engineer receives a configuration error. The catalog, schema, and table name are all correctly referenced. Which configuration requirement for the source delta table is most likely the cause of the error? Select one. Review the answer choices on screen. The correct answer is option A. CDF is always the prerequisite check for delta sync. Delta sync indexes on standard Databricks AI search endpoints require change data feed, CDF, to be enabled on the source delta table. CDF tracks row-level changes, inserts, updates, and deletes, so the index can stay synchronized with the source data as it evolves. Without CDF, the endpoint has no mechanism to detect incremental changes and the index creation fails. The column name _i.d is actually a reserved name in AI search that engineers must avoid, so using it would cause a different kind of error rather than the configuration error described here. Partitioning by the identifier column is not a requirement for AI search indexing. Source tables for delta sync must be delta tables registered in a Unity catalog schema, not files stored in a volume. Questions 11 to 15 tested LangChain retriever wiring. UC model registry aliases replacing legacy lifecycle stages, a second feature spec scenario with harder distractors, safety-critical recall at K, and CDF surfacing again as the delta sync prerequisite. Let us keep moving. Question 16. Underline the key phrase mentally. A generative AI engineer at an insurance company is deploying a customer-facing claims assistant through AI Gateway. The security team requires that personally identifiable information, including email addresses, social security numbers, and phone numbers, must never reach the underlying language model in raw form. However, the assistant must still be capable of generating useful responses to queries that happen to contain such information. Which AI Gateway guardrail configuration satisfies both requirements? Select one. Review the answer choices on screen. The correct answer is option D. Blocking kills the assistant. Redaction preserves its usefulness. PII detection with redaction satisfies both requirements simultaneously. It prevents raw PII from reaching the language model by replacing sensitive fields such as email addresses, social security numbers, and phone numbers with placeholders before forwarding the request, while still allowing the model to generate a useful response based on the sanitized content. PII blocking rejects the entire request when PII is detected, which means users who legitimately include personal context in a claims query receive no response at all, breaking the assistant's usefulness. Safety filters target harmful content categories such as hate speech and violence. They are not designed to detect or sanitize PII. Rate limiting controls how frequently requests are submitted but does nothing to protect PII that is already present in a request from reaching the language model. Now, question 17. This is a precision check. A generative AI engineer at Alderton Biotech has created a delta table of research article summaries in Unity Catalog and is attempting to create a delta sync index in Databricks AI search using managed embeddings. The call to create _delta_sync_index returns an error indicating the source table is incompatible. Unity Catalog is enabled and serverless compute is available. What prerequisite is the engineer most likely missing? Select one. Review the answer choices on screen. The correct answer is option A. Managed embeddings don't waive the CDF requirement. Delta sync indexes rely on change data feed (CDF) to track incremental changes in the source delta table and keep the index synchronized as records are inserted, updated, or deleted. CDF must be explicitly enabled on the source table either at creation time using TL properties or afterward with alter table set TL properties. Without CDF, AI search has no mechanism to detect which rows have changed since the last synchronization and cannot maintain an accurate, up-to-date index. Date partitioning is a performance optimization for query patterns and data pruning, but plays no role in the AI search synchronization protocol and is not a prerequisite for index creation. Publishing a table to an online feature store is a requirement for feature-serving endpoints, not for AI search delta sync indexes, which read directly from a Unity Catalog delta table. For delta sync indexes with managed embeddings, AI search computes embeddings from raw text columns automatically using the configured embedding model. Providing pre-computed embedding vectors in the source table is only required when building a direct access index, where the caller supplies and manages all embeddings externally. Time for another one. Question 18. Reason from the scenario. A social media company is building a policy enforcement pipeline that must analyze both thumbnail images and short video clips uploaded by users in a single model call. The engineer wants to use a foundation model API model that natively handles all required input modalities without any additional pre-processing steps. Which model should the engineer select? Select one. Review the answer choices on screen. The correct answer is option B. Video input eliminates all options except Gemini. Gemini 2.5 Flash is the correct choice because Gemini family models available through the Foundation Model API natively support all four input modalities: text, image, video, and audio. This native video support is the decisive differentiator that allows a single model call to process both thumbnail images and video clips without any additional pre-processing pipeline. Claude Sonnet 4 supports text and image inputs within the Foundation Model API, but does not support video as an input modality, making it incapable of natively ingesting video clips for policy analysis. Llama 4 Maverick similarly supports text and image inputs only, and cannot process video content without a separate frame extraction step that reroutes the workload outside the model's native capabilities. BGE Large is an embedding model that produces vector representations for retrieval and similarity search. It cannot interpret visual or video content, cannot detect policy violations, and cannot generate structured text output of any kind. This one's about input modalities. Let's build a quick tree to pick the right model. Imagine a policy team scanning 50,000 user uploads per hour, thumbnails and short video clips. They want one model call to check both. No frame extraction step, no extra pipeline, so the model must natively handle video. Claude Sonnet 4 takes text and images, but stops there. Video is out. Llama 4 Maverick is the same. BGE Large is purely an embedding model. It outputs search vectors, not policy decisions. Gemini 2.5 Flash is the only model here that handles text, images, and video natively in one call. The question tests exactly that. Video support is the deciding factor, not just being multimodal. Time for another one. Question 19. A generative AI engineer at Meridian Research has deployed a shared foundation model API endpoint through AI Gateway that is used by 3 data science teams. One team's overnight batch jobs have repeatedly exhausted the endpoint quota, blocking the other 2 teams during business hours. The engineer needs to prevent any single team from monopolizing the endpoint's capacity. Which AI Gateway feature addresses this requirement? Select one. Review the answer choices on screen. The correct answer is option A. Group-level rate limits stop overnight batch jobs from hoarding quota. Rate limiting in AI Gateway can be enforced at the endpoint level, user level, or group level, making it possible to cap the number of queries per minute or tokens per minute for each data science team independently. This directly prevents any single team's batch workload from consuming the full endpoint capacity and blocking other teams. PII detection and redaction protects sensitive data within requests and responses and has no mechanism to detect or throttle batch usage volume. Safety filters evaluate content for harmful categories such as hate speech and violence and cannot distinguish or limit high-frequency automated batch calls. Traffic splitting directs a configurable fraction of requests to different underlying model endpoints for A/B testing or gradual rollout scenarios. It distributes traffic across targets but does not cap consumption per individual caller or group. Time for another one. Question 20. Start with what the user needs. A generative AI engineer at Riverton AI is designing an evaluation framework for a customer support RAG system that returns up to 10 documents per query. The team has labeled a test set of queries with graded relevance scores from 0 to 3 for each candidate document, and wants a metric that captures both the intensity of relevance and how highly ranked relevant documents are. Which metric best meets these requirements? Select one. Review the answer choices on screen. The correct answer is option C. Graded labels plus ranking sensitivity means DCG, not recall. DCG at 10 is the appropriate choice when the evaluation set uses graded relevance labels and the quality of ranking order matters. It sums relevance scores across the top 10 positions using a logarithmic discount, so a highly relevant document ranked first contributes far more than the same document ranked 10th. The 4-point scale from 0 to 3 maps directly onto DCG's relevance grades, making it a natural fit. This makes DCG at 10 sensitive to both relevance intensity and ranking position simultaneously. Recall that 10 only distinguishes relevant from non-relevant and ignores ranking order. It cannot use the full 0 to 3 scale meaningfully. Precision at 10 also focuses on the proportion of retrieved results that are relevant rather than their ordering. Hit rate at 10 is the coarsest signal, treating any position in the top 10 equally and losing all grade and ordering information. Let's slow down here. The DCG metric is worth really understanding before exam day. Imagine you label 500 support queries. For each result you give a grade. 0 means junk. 3 means a perfect answer. You want a metric that rewards putting the 3s at the top. DCG, discounted cumulative gain, does exactly that. See how the score falls. A grade 3 doc earns 3.0 points at rank 1, about 1.9 at rank 2, around 1.2 at rank 5, just 0.9 at rank 10. Burying a great answer costs you real points. Hit rate only asks whether anything relevant showed up. Precision and recall ignore rank order completely. When the exam asks for graded intensity plus position discount, that's DCG. The answer is C. 3 takeaways from this session. First, delta sync indexes require change data feed on the source table. Without it, index creation fails immediately. Second, rate limiting at user or group level in AI Gateway caps the quota any single team can consume. Third, when evaluation labels are graded 0 to 3 and ranking order matters, DCG is the correct metric, not recall or precision. These aren't arbitrary gotchas. CDF requirements, alias routing, and gateway guardrails reflect the exact decisions you'll face in real production deployments. Read the docs once. Own this domain.